Right, look at this mess we made in the last section. We've been talking about linear problems, nonlinear problems, finite dimensional problems, infinite dimensional problems. What we haven't been speaking about is what kind of problems, what problems are we actually looking at? Okay, I mean we mentioned differential equations somewhere over here. And well, we mentioned integrations, so you could as well study integral equations or mixtures of the two or completely different equations. We will try to keep this open and flexible as long as we can, because this gives us more generality, and that's what mathematicians do. Okay, so what problems are we talking about? So when we say we keep it general, then we say that we take a linear operator A between linear spaces x and y, and we study three different problems. One of them is just linear equations. Well, ax equals b, as you usually call them in your linear algebra course. Second kind of problems is linear least squares equations. Let me write this out. Least squares equations. In German you sometimes say Ausgleichsprobleme, and you would abbreviate this as ax tilde b. Okay, and the third kind of problem is also one that you know from your linear algebra course. It's eigenvalue slash spectral problems. Ax equals lambda x. To be a bit more precise, one should actually say linear least squares problems, not equations, because it's not an equation, it's roughly equal sign, but well, people tend to say equations, but probably it should be problems. Okay, when you say these things, then one should explain what we mean. So x and y are vector spaces. We all know from linear algebra 1 or 2 what a vector space is, and we will recall that in chapter 2. What is a linear operator A? Maybe we should say that now. So what is a linear operator A? X to y. So far it's just a function taking little x's from x and turning them into little y's from y is called linear, and you call it linear operator or linear transform or linear whatever if, well, a of x1 plus x2 equals a of x1 plus a of x2 for all x1, x2, and capital X, and a of lambda times x equals lambda times a of x for all lambda in, well, it could be real or complex numbers, let me say reals for the moment, and x in x. Okay, if a has only one argument, then you usually drop the brackets. Let me try to erase them here. My eraser's broken. Okay. Right. So what this means is that your operator A is compatible with the operations plus and lambda times of your vector spaces x and y. We will talk about this in chapter 2 again. Okay, this is just for you to recall what linearity means. And sometimes one gives these two properties separate names, where you call this additivity, or the operator's additive, and this one you call homogeneous, or homogeneity is the word. Okay. So if you think of your operator A as a little black box, well, let me paint it black then. That takes little inputs x and produces an output that is then called A of x, then linearity simply means, well, let's read it out. Additivity, first of all, means that if you've got two different inputs, let's call them x1 and x2, and you add them before passing them through the machine, then what you get is just the output of x1 and x2 separately processed by the operator A, and then the result added. So you can add the inputs, and what you get is just addition of the outputs. That's what additivity means. Okay, and homogeneity is pretty much the same now with multiplication by scalars. So you could multiply your input x by 3 or any other little lambda, and then send it through the black box, and the result is just going to be 3 times the operator applied to merely x. So multiplication by 3 before leads to multiplication by 3 afterwards. Okay, well, that's what linearity means. In the end, of course, what you want is you want to combine these two rules. You want to combine additivity and homogeneity. So for example, if your little x is of the form, let's say alpha 1 b1 plus and so on alpha n bn, where b1 to bn is your basis, your basis elements, then applying the operator A to that x, which means sending this whole linear combination through the machine, means, well, sending each one of those through the machine and adding up afterwards. And this you could even simplify by getting little alphas out. So in the end you would just send b1, b2 and so on up to bn through your black box A, and then take the results, multiply them by little alphas and add up everything. And this is exactly what you learn in your linear algebra course, that it's enough to know what the operator does to your basis elements, and already you know what it does to an arbitrary linear combination of those. Okay, so maybe that helps. Maybe it's just additional complications. So some people find it helpful to think of functions and operators as little machines, little black boxes. Some others don't. Of course, you can pick what you want. Okay, so in your linear algebra course, you will have looked at these things, but then your dimension of x and dimension of the space y have usually been finite. One is M, one is N, and then A can be represented by an M times N matrix. That's not no longer true if you go to functional analysis. Let me just say not. So at least one of them is infinite, and that makes your matrices infinite, and that of course makes things tricky.